Black holes. They have to be the most perfect and definitely the most mysterious objects in the entire universe. From way out here, they seem almost simple, right? You can describe one with just its mass, charge, and spin. But what happens if you could actually go inside? What's really hiding behind that point of no return? Well, today, we're going to try and peel back that event horizon and dive into one of the biggest questions in all of physics. So, to really get a grip on this, we're going to zero in on this very question. Imagine we had an indestructible probe, something that could withstand literally anything. What would it actually see, what it would feel as it got to the very heart of a black hole? This mission, well, it's going to take us right to the edge of what we know, to a place where reality itself seems to just break. So here's our flight plan. First, we'll talk about why this journey is basically impossible with our current maps of physics. Then, we're going to cross that point of no return, navigate the seriously bizarre abyss inside, come face to face with the classical end of spacetime, and finally, we'll look at the radical new ideas that are trying to completely rewrite the laws of the universe. All right, to kick things off, you've got to appreciate that the inside of a black hole is the ultimate terra incognita, the ultimate unknown territory. It's the one place where our best theory of gravity, Einstein's general relativity, basically predicts its own failure. You've probably heard this analogy before, but it's perfect. The core idea is that mass tells spacetime how to curve, and that curvature, in turn, tells mass how to move. A star, a planet, even you and me, we're all making these little dents in the fabric of the universe. A black hole, though? That's not a dent. It's a puncture. It's a place where that curve becomes, for all intents and purposes, infinitely steep. Okay, so our indestructible traveler is now getting close to the black hole's edge. Now, this isn't some kind of physical surface you could touch or knock on. Nope, it's a boundary that is way more absolute. It's the event horizon. The best way to think about it is like this. Imagine you're in a canoe, paddling away from a massive waterfall. At first, you're fine. You can get away. But you know there's a point where that current is just moving faster than you could ever possibly paddle. For a black hole, that current is spacetime itself, flowing inward. And the speed limit you can't beat is the speed of light. The second you cross that event horizon, every single path leads in only one direction, down. And this is where we have to clear up a huge misconception. From our safe spot far away, we'd watch our traveler's clock just slow, way down because of the crazy time dilation. They would seem to get dimmer, more redshifted, and then just freeze at the edge forever. But for the traveler themselves, nothing. They would just sail right on across the event horizon in a totally normal amount of time. No bump, no signpost, no drama. The drama's all from our perspective. Okay, our traveler is officially inside. The laws of physics are the same, but the actual landscape of spacetime has been twisted into something utterly alien. So the pull of gravity on our traveler's feet would be exponentially stronger than the pull on their head. This difference would stretch them out into a long, thin strand of atoms. Yeah, just like spaghetti. Now, for a smaller, stellar mass black hole, this would happen before you even get to the event horizon. But for a supermassive one, you could cross the horizon just fine, only to face this stringy fate deeper inside. And now we get to probably the most mind-bending part of this whole journey. Outside the black hole, you can move wherever you want in space, right? But you're a prisoner of time. You're always moving toward the future. Well, inside, that logic completely flips. The singularity at the center is no longer a place you can try to fly away from. It's an event in your future. You are now a prisoner of space, being pulled to the center no matter what. You can no more avoid hitting it than you could avoid next Tuesday. It's just going to happen. So every path, every possible move now leads straight to the center. Our traveler is about to meet what general relativity calls the end of the line, the gravitational singularity. This quote really just cuts right to the chase. You see, physicists don't really think a point of infinite density actually exists in reality. What they believe is that the singularity is a warning sign. It's a sign that our theory, general relativity, has been pushed way past its limits and has officially broken down. So according to the math of general relativity, all the mass of that dead star gets crushed into a point with zero volume. And that means infinite density, infinite gravity, infinite space-time curvature. It means all the laws of nature that we know and love just stop making sense. So what does a catastrophic breakdown of physics actually mean for our traveler? This is the perfect analogy. When your calculator flashes error, it's not because you found some mystical infinite number, right? It's because you asked it a question it's just not programmed to answer. The singularity is physics basically saying the exact same thing. Error. New program required.
And that new program, well, it has to come from the other great pillar of modern science, quantum mechanics. To really solve the riddle of the singularity, we have to go to the quantum frontier.
Think of it like this. General relativity is our theory for really big stuff. Planets, stars, galaxies. And quantum mechanics is our theory for really small stuff. Atoms and particles. But at the center of a black hole, you've got a massive amount of stuff crushed into a tiny, tiny space. It's the one place where both theories have to work together, and right now, they just don't. They contradict each other, so we need a new theory to bring them together.
And this is where things get truly wild. I mean, to replace this idea of an infinite singularity, physicists have come up with some of the most mind-bending ideas you can imagine. So what would our traveler actually find at the center? Let's take a quick tour of the top contenders.
This first one is pretty radical, and it comes from a deep puzzle about whether black holes destroy information, which would violate a basic rule of quantum mechanics. As a potential fix, some physicists came up with the firewall. The idea? The event horizon isn't a calm doorway after all. Instead, it's a violent, blazing hot wall of energy that would just incinerate our traveler instantly. If that's true, the journey inside is over before it even starts. Okay, so another top idea, loop quantum gravity, says that spacetime isn't this smooth, continuous thing. No, instead, it's pixelated. It's made of these tiny, indivisible quantum loops. And if that's true, well, you can't crush matter down to an infinitely small point, because there's a smallest possible size for things. So instead of that smooth rubber sheet that can get punctured, imagine spacetime is more like a woven network of connected nodes, kind of like cosmic chainmail. As matter collapses, the network itself resists and pushes back with this incredibly powerful quantum force. Gravity gets ridiculously strong, sure, but it never reaches infinity. The divide by zero error is avoided. And the ideas don't stop there. String theory offers another cool alternative called the fuzzball. In this picture, a black hole isn't empty space with a point at the center. The whole thing is filled with a tangled ball of fundamental strings. Other theories propose that the collapsing matter forms a Planck star, an object that's unbelievably dense but still finite that might bounce back, maybe even into another universe. Look, whether it's a firewall, a quantum bounce, a ball of string, the goal behind all of these theories is exactly the same: to finally find a single consistent set of laws that describes everything in the cosmos, from the tiniest particles to the biggest black holes. It's basically the holy grail of modern physics. And that really leaves us with our final thought. The singularity isn't just some place where matter gets destroyed, it's the place where our current theories fail. It's like a giant signpost, pointing the way toward a deeper, more complete understanding of reality. It isn't just an end, it's the ultimate puzzle. So you have to wonder, is the center of a black hole an ending, or is it a brand new beginning for physics?